Hello and welcome to our broadcast titled Real-Time Metering with Redis Enterprise. It's my pleasure to introduce today's presenter, Roshan Kumar, Product Marketing Manager at Redis Labs. Metering is a common use case applied in rate limiting, traffic shaping, consumption-based pricing, resource, and activity tracking. Redis Enterprise simplifies implementation of metering not just through high performance and scale, but also through built-in data structures and commands that deliver the required processing. Today's broadcast is being recorded. Following today's event, an email with a link to the recording will be sent to you for sharing with your fellow workmates. We will be taking questions throughout the broadcast. There is a question and answer feature in the control panel you can use to post questions. Questions will be answered in the order that they are received. Thank you for joining us today, and at this time, I'll turn the broadcast over to Roshan. Roshan, take it away.
Hi everybody, good morning, good afternoon, or good evening, wherever you are. Today we have a very interesting topic. It's about metering. We have a very good agenda. We'll start with what is metering. We'll discuss some of the scenarios about metering and talk about the technical challenges that arise when you are developing solutions for metering. And then we'll see how Redis Enterprise addresses those technical challenges. And finally, we'll have a short demo of a simple cell rate limiter. We'll see how easy it is to develop a very simple rate limiting application using Redis as the database. Okay, let's start with what is metering. The dictionary definition is very straightforward. It talks about measuring time, distance, speed, or intensity of anything. So the key word here is measure. It's all about measuring. And the second part of metering is recording and regulating. So you measure stuff and then you regulate that stuff. So metering is not just about measuring, it also involves measuring and regulating stuff. And let's see what these things are, and let's look at some of the scenarios. One example is rate limiting. There are very popular APIs. Twitter developer API is one of them, and even Google has some public APIs. Now, these public APIs are rate limited. When I say rate limited, if you are a developer and if you develop an app to access these APIs, you can make only a certain number of calls in an hour. And if you exceed that number, then Twitter will stop serving you the response. So that is a rate limiter. And there are many public APIs, many public APIs that use rate limiting. And some of the, now why would a public API require rate limiting? They require it because if you don't have rate limiters, then it's very likely that the developers abuse the system and they take advantage and they eat up all the resources. And it's a cost, it's a burden on the cost, it's a burden on the infrastructure, operations, and everything. So having a rate limiter, it eases the burden and reduces the operational cost. Now, there is another scenario. We have a customer, Home Depot. They had this problem. The problem is they have many legacy applications or legacy solutions, and they have built in a lot of business logic into their legacy solutions, and it's very hard for large enterprises especially to disinvest from those legacy solutions. They have monolith databases that run heavy business logic, but the problem is their user base has grown so much, and the apps that access this legacy system have grown so much that the legacy systems, they cannot take this load anymore. So that's what is happening. So that's a big challenge. And one way they solved that problem is they put a rate limiter in front of these legacy systems. So they metered all the calls that went to these legacy systems. So they regulated how many calls were made in a second. They had a number like 20,000 calls per second or 15,000 calls per second. So they put a rate limiter in front of these legacy systems, and that way they were able to manage the load or any burst traffic that went to the legacy system. So this is another example. The third example is usage-based pricing. Now, this is a very common scenario these days. Pay-as-you-go is everywhere, whether you go with cloud services or any as a service. Wherever you have as a service, then it's very likely that the pricing is based on usage. And the challenges, there are many challenges here. Now, the usage is, there is no one variable. For example, in cloud computing, it could be your computational resources, your memory, your type of server, your bandwidth usage, and so on. So there are many variables, and your usage-based pricing is a combination of how you use all these resources. It's not just one resource. So you have to track multiple metrics, and the second problem is you need to have some accuracy, level of accuracy in tracking all the usage. Otherwise, you'll be billing lower than what the customers use your resources for, or you may be billing higher, which may hurt your credibility. And the last thing is you need a permanent proof of record for all the things that you charge for. Now, if you're charging based on CPU resources, then you better track all the CPU usage. Without having a permanent proof of record, it's really hard to bill against the usage of those resources. Right? And then traffic shaping. Now, this is very similar to the second scenario that we discussed. When you put a solution in front of legacy servers, you shape all the traffic, right? So that's one example. But there is more to traffic shaping. You may think of controlling number of packets in a pipe. When you're developing a solution with a limited bandwidth. So traffic shaping is extremely important. And there is another problem with traffic shaping, because now if you have limited bandwidth, and if the rate of arrival of all the messages of all the traffic is faster than how much your pipe can take, then you have to make real-time adjustments. So the key word here is real-time. So you have to make real-time decisions, and managing traffic in real time is a nightmare, especially at scale. So these are some of the challenges. These are some of the scenarios of metering, and we can go on and on. There are many more scenarios, but these are some of the common examples of metering scenarios. Now, the technical challenges. Now, let's see how traditional solutions try to address these challenges. Now, there is one scenario which is a very common scenario. Most solutions, they try to address all metering logic by having all the logic and all the counters in the app itself. Now, the problem here is there is no data persistence. If you are having all the counters, all the usage-based counting, everything in main memory inside app, and if the app fails, then you lose all the data that you have tracked so far. So you cannot really make any decisions. If your billing is based on usage, you lose all the data and you won't be able to bill. So there is no data persistence, and failover is a problem. Now, you could argue that you can have app failover, but to have an app level failover, it's really it's a very complex solution, and you can always push the data to. You can always argue that you can push the data to a database that can do this easily. So you come with scenario 2, where the architects decide to push the data to a database. This is very straightforward and logical. So the metering logic is in the app, but all the counters and all the tracking is done in a database. Now, there are some problems here. First of all, if you are using a traditional relational database, then it's not really lock-free. And if multiple apps or multiple solutions use the same resources, same counters, then you should have a way to synchronize all the updates made to these counters. So that becomes a nightmare. And also the databases, they're just tables, and you don't have any built-in data structures to address all metering scenarios. You cannot really count a large number of objects, large number of unique objects, if at all your metering solution requires them. And scaling becomes a problem again because you are limited by how many operations you can run per second, how many write operations you can run per second. So typically what you do is you add more resources, more servers. So you'll have a very heavy solution in the back end to deal with the databases. So Redis Enterprise for metering. Now we talk about Redis Enterprise. It addresses all these challenges. First of all, you don't have to have the data structures in the app. Now you can have all the data structures in Redis itself. And what's better is Redis itself provides you with a lot of data structures like lists, sets, hyperlog logs, and there are many, many data structures that will help you in collecting all the data you need. And also it has counters. You can have atomic commands. Now, Redis provides you with atomic commands, and you can update all the counters without really needing a lock mechanism. So it makes your architecture very easy and straightforward. And also Redis is a very lightweight database. We'll talk more about that in a while. It's extremely lightweight, and you don't need a server-heavy environment. You can develop with very minimal number of resources. So what is Redis? For those who are new to Redis, let me take a minute and explain to you what Redis is. Redis is the leading in-memory database platform. It is the most popular database on Docker. It is the most downloaded database on Docker. There are about 400 million downloads in Docker environment. It is open source, and it's extremely powerful. It operates about 1 million writes per second with a modest server, and it's used in many real-time analytics use cases, and also you can do 1 million writes per second and also 1 million reads per second. So you can have heavy number of reads and writes at the same time, and it's extremely lightweight. Now, Redis Enterprise. Now, even before I go to Redis Enterprise, the Redis Labs, it sponsors the Redis open source database. It sponsors the project. Now, Redis Labs also offers Redis Enterprise. Redis Enterprise is built on top of open source Redis. Now it helps you scale with Redis. It puts a layer on top of open source Redis, and you can have multiple shards, and it provides you an auto-scaling, high available environment with a Redis database. So when you're developing applications, you develop as if you are developing to a Redis database, but in the back end, Redis Enterprise allows you to scale without any effort. It helps you to scale, manage all the shards. It has a UI through which you can manage all your shards, all your Redis resources, and it helps you grow without much problem. Right? So how does Redis help in metering? There are 8 reasons. I will go through each reason. Now, first of all, high performance with low latency. We have some benchmarks here. Now, Redis is benchmarked to support more than 1 million write operations per second. These benchmarks are done by a third-party company called Avalon, and they showed that Redis does the most write operations per second with the least latency. So that's the benchmark you see on the screen, the chart that's on the top. Now, there is a chart at the bottom, and this is a very interesting story. It is about how many servers you need to perform 1 million writes per second, and this particular chart is based on the experiments run on Google Cloud Platform. It all started with a blog. Google published a blog where they said you could run 1 million writes per second on a Cassandra platform, and they published all their metrics, and they showed that you could do that with 300 servers on Google Cloud Platform. Now, Couchbase took that challenge, and then they showed that you could do the same benchmark with just 50 servers on Google Cloud Platform. Now, we at Redis Labs, we also did the same experiment, and guess what? We were able to do 1 million writes per second with just two servers with Redis Enterprise. So, as I said earlier, Redis is a lightweight database. It's extremely efficient, and it's extremely fast, and it provides a lock-free environment, and it makes all the writes super easy and super fast. Now, with this said, Redis supports high volume of data, so it supports fast data ingest. Now, in counting or metering, wherever you have a lot of data arriving in bursts, Redis is extremely efficient. It can collect all the data without losing data. So it can support extremely high volumes of data arrival, and with extremely low latency, with sub-millisecond latency. So this is reason number one. And reason number two, we have atomic commands for counting. So what it means is you don't have to get the data to your app, modify the data, and push the data back to the database. It's all done in an atomic way. You can just run one command to increment a counter, and you can increment a key, or you can increment by a number, or you can decrement. And if at all you have a hash object, you can increment or decrement objects, the values inside the object itself, and you don't have to load the whole hash object into your application. And also a trivia here, the biggest number you can store in Redis is to the power of 63 minus 1. So this is the number, and I did some math here, and if you update a counter every millisecond, it takes about 300 million years to reach this big number. So it's about 300 million years if you update every millisecond. And there is built-in time to live. This is a very interesting feature in Redis. You can expire the keys. How does it help metering? It helps in metering to limit all the resources based on time. We have a customer, Roblox. They have a gaming platform. They have about 50 million users, and at times they have more than 1 million users who simultaneously use their system. It's a gaming platform, and they meter all the connections they have. So they store all the connections as objects in Redis, and guess what? They have a TTL on all the connections in Redis. So it's extremely efficient. They saved a lot of money on the resources, and it made their architecture so easy and simple. So they just rely on Redis. They depend on Redis to time out all the connections, and they are able to manage millions of connections. And it's a metering scenario once again, and they expire all their connections automatically. And there are many commands. There are many ways to expire keys in Redis, and you can see on the screen we have you can expire based on number of seconds, or you can even expire based on milliseconds, and there are a few commands to do that. Now, once again, data structures. This is one of the strengths of Redis. Redis is like a Lego. It's like a Lego building blocks for programmers, and it is a Lego building blocks because there are so many data structures that are built in. There are lists, sets, sorted sets, hashes, and also some new data structures like hyperlog logs that are very efficient in storing millions of unique objects. And also it provides bitmaps and many other things. Now, another cool thing here is Redis also provides commands that are optimized to run efficiently and optimized to run very fast. So if you have a list of million objects, and if you run len, L-L-E-N, so that is the command that gives you the length of the list, it just returns the value in sub-millisecond. And same with set, we have a command called scard. It gives you the cardinality of a set, or a zcard, which is cardinality of a sorted set. So it helps you count millions of things in sub-millisecond, and this helps you make decisions in split seconds in real time. Now, data durability. Now, we talked about usage-based pricing, pay-as-you-go, and freemium models, and there are many tiered pricing models. Now, all these models, they depend on tracking the usage, and all the billing is made on how well or how much the resources are used by the consumers. Now, we also talked about permanent proof of record for all the usage. Redis makes the data durable. There are many ways to attain durability in Redis Enterprise. Now, Redis Enterprise has in-memory replication. So you can have two nodes of Redis, and they replicate data in memory, and in-memory replication is faster than disk persistence. And if at all a node should go down, the data is you have a copy of that data in a secondary server in a split second, in a few milliseconds. So that is the recommended way with Redis Enterprise. And in Redis, if you are with open source Redis, you still have data durability through persistence, and you can use append-only file, or you can do snapshotting to get data persistence. And also Redis Enterprise also does replication, and also it can maintain copy across WAN. So you can see on the screen that Redis Enterprise, it does compression and deduplication. So it does WAN optimized replication. So if you are doing replication across geographical areas, then we have WAN optimized replication. Now this is a very interesting point, the sixth one, high availability. Now when your business relies on metering, if all the billing is done on metering, it's extremely important to have your system up and running all the time. If your system goes down, then it impacts your business. Redis Enterprise, it promises high availability. And as you see on the screen, your application, when you're developing your apps or your solutions, they all talk to a proxy server, and each node can have a proxy, and you talk to a single proxy, and the proxy, it's a zero latency proxy. We'll show in the next screen how the proxy works. But your application talks to the cluster of Redis Enterprise as if it were a single instance of Redis, and the proxy will send that information or send your request to the appropriate shard all in real time. And it gives you high availability, and your business can completely rely on Redis Enterprise for high availability and always on capability. And another interesting point here is open source Redis is a single threaded system. So if you are running open source Redis on a 16-core CPU, it just runs on one core. It doesn't give you the highest throughput. Now what Redis Enterprise does is it creates 16 shards for you, and each shard will run on a separate CPU, on a separate core of your CPU. So if you're running your system, if you're running your database on a 16-core CPU, Redis Enterprise will ensure that you can run open source Redis shards on 16 cores, and that gives you the highest throughput. So you're not wasting your CPU cores. Right? This is another point, a LockFree architecture. This extends our discussion from the previous slide. The proxy server, it is a multi-threaded server. So if you have an application with multiple threads, or if you have multiple processes talking to the same proxy, the proxy itself is a multi-threaded server, so you can so it can have multiple connections, and it can take requests from multiple connections in parallel. And what it does on the other side is it multiplexes all the requests coming in, and it does everything in with zero latency. It pipelines all the commands that go to the Redis cluster. It manages all the pipelines. It does all the pipelining, and it streamlines all the requests coming in, and it makes it very efficient for you. So what does this mean for you? If you're developing an app, if you're architecting an app or a solution, you don't have to worry about managing all the threads and synchronizing all the threads while updating the data. It's all done by Redis Enterprise. It's all automatically done. So we promise serializability with the lock-free architecture. Right. And the last point here is active geo distribution. Now with Redis Enterprise 5.0, which is available for preview right now, and it will be available. The GA will be available very soon. We have an active capability. So this is a new feature that we are introducing in 5.0, and the nice thing here is the active solution is based on conflict-free replication data type, or CRDT, and we call this a conflict-free replicated database. Now, the good thing here is all the updates are made locally, and all the instances that are distributed geographically, they synchronize, or they converge with strong eventual consistency. So it is not just eventually consistent; it is strong eventual consistency, and it's extremely efficient. I'll give an example. Suppose you have a family plan for your mobile, and one of your family members goes to, let's say, travels from one continent to another continent. All the usage can be updated locally. You can have a local Redis Enterprise instance that is metering all the usage, and you have the latency of a local server, but in the back end, Redis Enterprise will ensure that all the data gets synchronized with strong eventual consistency. Now, this helps. You can avoid all the round trips that happen, so you don't have to wait for the other server across the continent to acknowledge that it has received your data. Now all the data is synchronized or converged in the background. Right. So if you have any questions, please post your questions in the questions folder. And let me see. There are some questions. Do you have any benchmarks comparing Redis to Map or DB or MongoDB? We have some benchmarks. We have published some benchmarks on our website. You can go and see. But one thing to note here: Redis is an in-memory database. It's extremely fast. We are talking of millions of writes per second. And when you talk about disk-based databases, it's not really a good comparison, because the analogous here is we are comparing race cars against trucks. Now, disk-based databases cannot compete in performance when it comes to in-memory databases, but there are still some benchmarks. You can see some benchmarks against other in-memory databases on our website. Now, there is another question. Can I put TTL on the objects that are inside the data structures? Okay, the question is about, let me go to that slide here. So it is about built-in time to live. You can see this on the screen. The question is, can I put a time to live on the objects inside the data structures? You can put time to live to the keys, and you cannot put time to live on the objects inside the data structures. For example, if you add an object to a list, you cannot put a time to live on the object inside the list. but you can put a time to live on the list itself. I hope that clarifies your question. But this is in the roadmap, so we don't have that feature today. We can put time to live only on the keys, but not inside a not to an object inside inside a data structure. Okay, let me go back to the present. There are a few other questions. I'll take those questions towards the end. Now what I'll do is I'll do a very quick demo of a few things, and I hope that will clarify some of the questions. So let me see, and okay, this is the first one here. So before I do that, my demo setup is very simple. I have a local Redis instance running on Docker. You can see that on my screen, and I'll do some demo here just using the command line interface. And the first demo here is how do I use time to live? I think there was another question about time to live, so hopefully this will clarify that question. Now, how can I use time to live for metering? Now, here is an example where I'm using time to live to block multiple attempts. Now, you can, in this example, I'm having a solution where I'm allowing 3 times. Let's say I can allow 3 login attempts in 5 minutes or 5 seconds, let's say, for the sake of for example. So what I can do is I can have a key. In this case, I'm doing a set user login attempt. I'm just making up a user here, 1, 2, 3, 4, and then I'm setting 1 as a counter, and the time here is I'm setting a time of, let's say, 10 seconds. So this is the first set in here. So I'm getting some error here. So in a sense, I'm trying to get a user ID here. So let me go ahead. So let me see, I got the syntax wrong. So I'm doing a set. So let me see the set command here. So I can do a set value and seconds. So set and expire. And do set user 1, 2, 3, 4, and then expire. Okay, so here I'm setting a value to a user, and that will expire in 10 seconds. Now, if I do a time to live on uset 1, 2, 3, 4, so that will, it has already expired. So so I can do more login attempts. So the idea is if I give a higher one here, and if I do a time to live on this user, so there's still 98 seconds left on this key. So in 98 seconds, I'm setting up a counter for 100 seconds, and I can have a logic around if the key is still alive, then I'm still counting how many attempts are made on this login for this user. I can do a time to live again. So I have 76 seconds left on this particular user. So I'm still counting how many login attempts have been made on this user. So it is here, and I can do an increment on this. So I can do an increment. If the user makes the second login attempt, I can do increment uset 1, 2, 3, 4. All right. So now it is the second attempt, and on the third attempt, I can do another attempt. Now I can see the idea. The logic here is if the user is still set, if the user is still there after third attempt, you can see if there is still time to live for this user. Let me see time to live. So there are still 25 seconds, and you can build a logic around this and say there are 3 attempts made on this user already, and this ID is still alive. So I cannot make any more attempts, any more login attempts on this user, and you can error out. So that is the idea. You can build logic around this. Right? Or I can do an expire. Use set 1, 2, 3, 4, and I can put 5 seconds instead of 25. So it's already expired. Okay, and then the second example I have here is this is a hash data structure, and I think there was a question also around can I increment an object inside a hash data structure? Yes, you could do that. All you have to do is use h increment by, or you can do h increment by float. So if you have a hash data structure where you have, in this case, you have a customer billing information and you're tracking usage and cost, you don't have to load the whole customer information into your app. You can just use h increment by, and then you can increment by whatever amount. Right? And I'll go to the next demo here. This is a demo I have on my laptop. So I'm going to run the demo on Eclipse. The idea here is I'm going to show 3 types of rate limiters. One is a uniform rate limiter, and a bursty rate limiter, and then I'll show you a simple rate limiter. I'll do a demo. So the idea here is in a uniform rate limiter, you have a window, and within window you have the number of actions you can have within that window. So in this case, I have a window of 4 seconds, and I can have 4 actions in 4 seconds, which means I can have 1 action every second. So it is uniformly distributed, and the way it works is if I make more than 1 request within a second, that should time out. So let's see here, and I have 4 arrivals. I'm making 4 calls. Arrival is a call. You can see 1, 2, 3, 4, and the first one arrives at 0th second, and the second one I took off the sleep time here, and it is arriving immediately after the first one, and the third test arrives after a second. I'm putting a thread.sleep, and the fourth one arrives after 3 seconds. So the hypothesis here is the first one should return true, and the second one should return false, and the third one should return true, and the fourth one should return true. So let's see what happens, and I'll show you how it is done. Yep, so you can see that's exactly how it is done. The first one is return true, second one is false. That's because I have a window of 4 seconds, and I can take 4 actions in those 4 seconds. And how it works is I'm calculating the interval, the value of interval, and after that I'm putting a TTL. I'm checking a TTL on the key. And how do I set the key? I set the key for the first time when I return true, and for all subsequent calls I see whether the key exists and if there is a TTL on the key, and if it is greater than 0, then I don't accept this arrival, the cell arrival. So it's a very straightforward one. So the idea is to spread all the calls uniformly. The other one is bursty rate limiter. Here the idea is you can have a large window, and you can support bursts of data. It is not uniformly spread out as we had in the previous example. So in this case, I have a window of 10 seconds, and in this window of 10 seconds, I can have a maximum of 10 actions. So I can support 10 arrivals. But I don't care whether those 10 arrivals happen within the first millisecond or whether they happen during the 9th second. So it is not uniformly distributed. So let's see how it works. Now in this case, you can see here, all of them should return true. So in this case, you can see all of them are accepted. The idea again here is very straightforward. We put all the arrivals into a sorted set, and also we put a timestamp against the sorted set, and we collect all the calls that have come in the window. And if we have fewer number of calls within the window, we accept it, and if it exceeds limit, then we don't accept the call anymore. Now, with this, we build a rate limiter. Now, this is a simple rate limiter. And in this example, I have a window of 20 seconds. And in this 20 seconds, I can have 20, let's say 20 calls. So I can make 20 calls. And this is a rate limiter where I'm doing traffic shaping. So I have 10 tests, 10 arrivals that happen almost simultaneously, one after the other within split millisecond. But the output is staggered. So the output will happen one every second. So this is a traffic shaping example. So let me walk you through this. So you can see all the inputs happen in the first second, but outputs, they're still running. They're all happening one every second. Now what happens if within the same window, if I can support only 10 actions within the window of 20 seconds. So you will see a slower output. So all the input happened very fast, and you can see the output is still going. It is one every 2 seconds. It's still going very slow. And the way it works is, again, there is a simple cell rate limiter, and we are managing all the arrival, and all the arrival, we push that. You can see this L push. So this pushes all the cells that arrive to a list in Redis, and there is a separate thread here. You can see a run method here. I'm pulling all the cells. I'm doing an rpop, and then I'm using a uniform rate limiter, and I'm checking whether it is okay to take action on this cell. So you can put your own logic here, and I'm doing some traffic shaping here. Okay, so this is an example, and all these examples are on GitHub. So you can go to Redis Labs demo on GitHub, and you can download these examples. And again, these examples are just examples and not really tested for production. And if you're developing something, you can get some ideas here and make sure you develop and test before you put things to production. Okay. Now I'll take more questions before I end. I think there are a few questions. Okay. Some of the questions here. Let me open that. Just give me a second. I'm trying to open the questions dashboard. Okay. There's a question, can Redis Enterprise be used on-premise, and is there any kind of integration support plan for proof of concept? Yes, Redis Enterprise can be used on-premise, or if you have a private cloud, you can use it in your private cloud. And also there is a trial. You can go to our website and download Redis Enterprise, and we support it on multiple platforms. So you can go to our website, and you can download Redis Enterprise for trial. And if you run into any problems or if you have any questions, you can contact us. And in my thank you slide, I had a contact us email address. It's expert@redislabs.com. So you can send an email to expert@redislabs.com, or you can contact me, Roshan@redislabs.com, and I'll put you in touch with the right person. Right. Is there any way to identify keys which do not expire where number of keys are huge? Okay, let me understand the question. The question is there any way we can get all the keys that have not expired? Right now, we don't have a way to do that. You have to check all the keys individually, and we don't have a query mechanism. With that said, Redis has other data structures that allow you to do that. For example, there is a sorted set, and if you want to know all the keys that are valid, what you can do is you can put those keys in a sorted set, and you can sort against timestamp, and you can run a query. You can do a Z-range query. You can go to Z-range, and you can do a Z-rev range. So there are multiple queries that you can run on sorted sets, and you can run a query and find out whether the keys are still alive or whether they have expired. Is your Java code available for download? Yes, it is available. As I said, you can go to GitHub, Redis Labs demo, rate limiter. You can get that. Oh yeah, I see that you have seen it. You have acknowledged it. Thanks. And then let me go to other questions here. Do you have a comparison with Oracle Coherence? Yeah, we have some benchmarks with Oracle Coherence, and as you can guess, we are much faster than Coherence. Again, go to our websites. You can go to our benchmarks page, and you can find information. And if you cannot find any information, feel free to contact us, and we'll send you the right information. The next question is, does proxy support Tomcat Java client? Oh yeah. Look, more than Tomcat Java client, you don't need a. I don't know what you mean by Tomcat Java client, but we do support Java client. There is a Redis library that will allow you to talk to any Redis. There is a Java library, and for Redis Enterprise, it is the same library that you use for Redis. You can use Redis library, and there are multiple Java libraries, so you can use any of them. We support all of them. So is the scale you talked about 1 million per second is for standalone instance or a cluster? This is a good question. The 1 million writes per second that we talked about, it is for Redis Enterprise. It is for Redis Enterprise cluster. And as I said earlier, Redis Enterprise, it gives you the highest performance. We run a shard against each CPU core, and that's how we get the highest throughput. So if you have 16 core CPU, we run 16 shards to give you the highest throughput, and we route all the questions. The proxy, the zero latency proxy routes and pipelines all the question to the right shard. So we manage that in the back end. I hope that answers your question. And the next one, what is the time for implementing Redis in an existing organization? Well, it's a very straightforward. It should be a very straightforward integration. It depends on how big of an implementation you're looking for. Usually, we have seen customers who have implemented Redis in a few days, and for some large deployments, it has taken few weeks. And it's not definitely months. It is few days to weeks. You can get started very soon, very quickly. And if you have any questions, you can always contact us. We are more than happy to help you. Okay, there is another question. Will the HA solution work with .NET Stock Exchange client? Yes, we do work with .NET Stock Exchange client, and we have many customers who are using .NET client and the Stack Exchange client. And if you have questions, again, you can contact us. Can we replicate data between different data centers? Oh yeah, we have many customers who are doing that. We do cross data center replication and cross cloud replication, and also, as I showed you, we also do WAN optimized replication. So that's absolutely possible. And when I say we, I'm talking about Redis Enterprise. It's absolutely possible. The next question, does open source clustering add extra latency in serving each request? Now, in open source, you should know that you are managing all the sharding. That you should understand. So it is not, you don't have a proxy that comes with Redis Enterprise. So it all depends on how you manage the shards and how you cluster. So it's all in your hands. So the overhead is in your hands. So you need to run benchmarks yourself to answer that question. So it depends on your implementation. Right. Okay, so let me see if there are any other questions. Okay. And then the other question I see here is, we use Cassandra for metering scenarios. How do you compare yourself with Cassandra? Now, again, I have to go back to my benchmark that I showed you earlier. So let me show the benchmark here. Cassandra is a server-heavy system, so you need a lot of servers to achieve the throughput, the kind of throughput that we deliver in Redis. So that should answer your question. And also Redis has many inbuilt data structures, many powerful data structures. With Redis, you get many more advantages. You get data structures, you get the lock-free environment. It is lightweight, extremely efficient, and we also have the least latency. So if you are making any real-time decisions in metering, then Redis is perfectly suitable for your real-time metering solutions. There is another question. How does HA balancer work? Does it require virtual IP or is it managed by client libraries? Now, your clients, they talk to Redis Enterprise as if it were a single instance of Redis. So the load balancing, everything is managed on the Redis side. The proxy, it does everything for you, and it is completely transparent to the application. The application doesn't need to load balance at all. So it's all done by the proxy. So that is one of the benefits of Redis Enterprise. I hope that answers your question. And the last question here I see is advantages of Redis PubSub over any other queues like Kafka. Well, we had a separate webinar on this very topic. You can go to our website and look for a white paper on fast data ingest, and we discussed this in length. Now, Redis PubSub has many advantages. It's extremely lightweight, and if you want, there are many other data structures in Redis that will help you with fast data ingest. And also, there is a Redis streams data structure that is in development right now, and we are expecting to get Redis streams data structure into Redis very soon, and that will have many capabilities that are missing today. So stay tuned and look for Redis streams data structure, and I hope that answers your question. Who did the benchmark of Cassandra versus Redis you mentioned earlier? Okay, this is another interesting point. Now, all this is on Google, on Google's blog. In fact, you can go to our site and find pointers to all the Google blogs. Now, Google did the benchmark for Cassandra. So Google showed that you can do 1 million writes per second with 300 servers. It's on Google blog. So all these benchmarks are published by Google on Google blog. Right? I think that was the last question I have here. Yeah, thanks for all the questions. Thanks. And if you have any more questions, feel free to contact us. And thanks a lot for attending this webinar. Bye-bye.
Hey, Roshan, thank you for sharing how Redis Enterprise enables real-time metering. So that takes us to the end of another broadcast. And on behalf of the entire Redis Labs team, thank you for joining us. An email will be sent with a link to the recording of today's broadcast. Join us again for our next broadcast. Visit redislabs.com/webinars and register today. Until next time.